an RC circuit. And in this, so for here we have a 5-volt source, a 300K resistor, a 10 microfarad capacitor, a switch, and the switch closes at t equals 0, and a 150K ohm resistor. So in this problem, we want to know what is the voltage across the capacitor for all time t. So let's take this, set up the circuit in 2 stages. So the first stage we're going to look at before the switch is flipped. Before the switch is flipped, we have an open circuit here, and that means that we have simply a resistor and a capacitor. And this capacitor, since the circuit has been running for a really long time for t less than 0, the capacitor is filled up. And for filled capacitors, we can replace those with an open circuit. So really quickly, we know that there's no current because of the open circuit, so this top node has to have a voltage of 5 relative to this bottom node. So the voltage across here, Vc for t less than 0, is 5 volts. Now we have our switch flipped. There's kind of two, so now that our switch is flipped, we have our voltage source, resistor, capacitor, and our parallel resistor. 5 volts, 300K, 10 microfarads, and 150K. So how do we analyze this circuit now? Well, we can set up a KCL at this node, and then use the currents, calculate the current in this top branch, the capacitor branch, and this resistor branch. So let's go ahead and do that. So if we kind of blow up this node here, we know that the voltage at this node is Vc, and the voltage at this top node is 5, and then we have our resistor in the middle. So the current through this resistor is 5 minus Vc over 300K. And similarly for this branch, we know that the voltage is Vc here, and the voltage is 0 here. And so we know the current over across the resistor is Vc minus 0 over 150K. And finally, for the bottom branch, the current through a capacitor is the capacitance times the change in voltage. So we can write our KCL, so the sum of the currents in have to be equal to the sum of the currents out. That tells us that we have 5 minus Vc on the left side over 300K. And on the right side, we have Vc over 150K plus this 10 microfarad capacitor times dVc dt. So let's, so now that we have our our KCL equation, we can, and it's a first order differential equation with a constant forcing function or a constant source on it. We can rewrite it in terms that we've seen in the lecture slides. So let's go ahead and do that. So by moving our equation around, we get dVc of t dt plus 1 times Vc of t equal to 10 e to the negative, 5/3 equal to 5/3. So, so this is our differential equation for that node, and it describes the currents entering and leaving that node. And we also know that Vc at t equals 0, right when the switch flips, is 5 volts. So using the formula that we have in the notes, Vc of t is equal to 5/3, the k over a, times 1 minus e to the negative a, which is 1, times t, plus the initial condition, 5, times e to the negative at, which is just t. And this is valid for all time t after 0. And we can kind of simplify that in one more step. So Vc of t is kind of 5 for t less than 0, and 5/3 plus 10/3 e to the negative t for t greater than 0 after the switch is flipped. Let's go ahead and graph that solution. So the voltage starts at 5, and this extends out to the circuit's been running for a really long time, so this gets extended out to the left. And we know that the circuit ends up at 5/3 because as t goes to infinity, this term drops out and we're just left with 5/3. So it kind of approaches this level here. And in between, we have this transient response of 5/3 plus 10/3 e to the negative t. So this there's an exponential curve that connects these 2 points. And we know that the switch flips at 0, and 1 second later, if we plug in 1 here, we drop significantly in our value, and this kind of value here, after one time step, is 2.89 volts. And if we actually look at our circuit, we can kind of see where this -1 comes from. For RC circuits, we can calculate a tau constant, which is equal to RC. And this RC, the R for the C, is the parallel combination of this 300K and 150K. So when you combine those 2 parallel resistors of 1 over 300K plus 1 over 150K and multiply it by our 10 microfarad capacitor, you get a time constant of 1 second. And that's exactly what shows up in our differential equation here. So in this problem, we looked at an RC circuit with a switch, and we analyzed the circuit before and after the switch, and then calculated the transient response, and then plotted the steady state before the switch was flipped, the transient, and then the steady state after the switch was flipped.